Section 1. The brain's surprise detector, or as neuroscientists call it, the mismatch negativity response. Think of mismatch negativity, or MMN for short, as your brain's automatic nonverbal alarm system. It's a negative going wave in brain activity that peaks really fast, just 100 to 200 milliseconds after a sound breaks a predictable repeating pattern. It happens right near the hearing centers of your brain, alerting you to unexpected changes even if you aren't paying attention at all. When that predictable pattern breaks, boom, the brain generates this massive electrical spike.
But why does this actually matter? Well, the MNN is fundamentally linked to what early psychologists like Pavlov and Sokolov called the orienting reflex. And this is an absolute evolutionary survival necessity. Imagine our ancestors out in the wild. Detecting the sudden snap of a twig in a quiet, predictable forest environment could literally mean the difference between life and death from a hidden predator. This reflex causes sudden, intense physical changes. We're talking shifts in skin conductance, heart rate fluctuations, and an involuntary reorienting of your attention. It actually halts whatever physical activity you're doing so you can quickly assess the threat. The MMN is that vital neural spark that ignites this entire survival reflex.
Section 2. The oddball paradigm, testing the brain's alarm.
So how do neuroscientists actually measure this invisible alarm system in a lab? They use something beautifully simple called the oddball paradigm. First, you repeat a frequent standard tone. Let's say it's just a simple beep, beep, beep. Doing this over and over causes the brain's response to adapt or habituate. It basically gets bored of the repetition, and the electrical response flattens out. Second, you randomly throw in an infrequent deviant tone, maybe a boop, with a probability of just 10 to 20%. Finally, using EEG or MEG sensors placed right on the scalp, researchers measure the resulting electrical activity. The standard tone gets a really quiet response, but that rare deviant tone, it triggers the massive MMN spike.
Okay, so we know the phenomenon exists, and we know exactly how to measure it. But here is the pivotal question that completely divides the neuroscience community. How does the auditory cortex bind this information over time to actually produce the MMN? I mean, how does the brain hold on to the memory of the standard tone long enough to know that the deviant tone is in fact different? This leads us straight into a grand scientific debate over the underlying mechanics.
Section 3. Theory 1. Neural fatigue, also known as the adaptation model.
This first contender relies on a localized bottom-up process. To really grasp it, we need to define short-term synaptic plasticity, or STP. This is the temporary altering of synaptic strength based strictly on what a neuron just did, and it lasts anywhere from tens of milliseconds to maybe several seconds. Now, it is absolutely crucial to understand that this is a temporary, fleeting change. This is entirely distinct from long-term Hebbian learning, the famous rule that neurons that fire together wire together, where synapses are permanently altered to form memories over months or years. Nope, STP is just a short-lived memory trace. When a synapse is used repeatedly in super quick succession, it undergoes depression. It gets temporarily weaker because it literally needs time to refill its chemical messengers.
A really great way to picture short-term synaptic depression in action is the neural fatigue analogy. Think of it exactly like a tired muscle. The specific neural pathways responding to the repetitive, standard tone are being used over and over again. They become totally exhausted and their signal weakens. However, the distinct neural pathways tuned to the new and frequent deviant tone haven't been used yet. They are totally fresh. So when that deviant tone hits, these fresh pathways fire a massive unadapted signal. In this view, the MMN isn't some special surprise calculation sent from higher up in the brain. It's simply a fresh group of neurons shouting over tired ones.
Section 4. Theory 2. Predictive coding and top-down inhibition. Now we pivot to our second heavyweight theory, which focuses on top-down inhibition. Predictive coding suggests the brain isn't just passively waiting around to hear sounds. Instead, it actively constructs generative models of the sensory world, constantly sending top-down inhibitory signals to suppress responses to sensory inputs it already predicts. This model implies that the brain is always trying to achieve this calm, flow state with its environment. Think about the rhythm of running, swimming, or playing music. When the brain's predictions get it right, the cortical Cs stay perfectly calm. When the standard tone repeats, the higher cognitive areas essentially say, hey, I know what's coming, don't bother reacting, and they cascade these inhibitory signals down the processing hierarchy to quiet the auditory cortex.
To ground this abstract concept, let's use the overconfident psychic analogy.
Imagine the brain's generative model is an overly confident psychic. This psychic predicts the standard tone over and over again and proudly suppresses the brain's reaction. But when a deviant tone hits out of nowhere, the psychic's prediction fails spectacularly. The brain gets shocked by the unexpected event, which generates a massive prediction error signal. And according to this theory, that error signal is exactly what we are measuring as the mismatch negativity.
Let's clearly contrast these two camps to really see the fundamental difference in direction and mechanism. Neural fatigue is purely a bottom-up process. It relies on localized synaptic weakening based entirely on the recent physical history of the stimulus. In total contrast, predictive coding is a top-down process. It's driven by inhibitory prediction signals generated by higher cognitive models actively trying to guess the future.
So to summarize this scientific boxing match, the direction is fundamentally opposite, bottom-up versus top-down. The mechanisms completely clash, synaptic depression versus generative models. And ultimately, they disagree on what the MMN actually is. Is it just a delayed, enhanced response from fresh neurons, or is it a dedicated, higher-level prediction error signal? Both of these theories are super compelling, but the plot is about to thicken.
Section 5. The Missing Sound Mystery, or the Stimulus Omission Challenge.
Just when we think we have everything figured out with neat scientific models, the brain throws a massive plot twist our way. We call it the stimulus omission effect. Researchers discovered that a massive MMN response is elicited even when a tone is entirely skipped in a fast-paced sequence, leaving absolutely nothing but silence. Imagine a rapid beat, beep, 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 and then suddenly, nothing. At the exact millisecond that silence occurs, the brain generates a huge electrical spike. The absolute crucial point here is that the brain reacts violently, not just to a different sound, but to the total, absolute absence of a sound.
And this brings us to the predictive coding problem. For predictive coding to work as it's currently formulated, it actually requires a physical stimulus entering the ear to miss the brain's prediction. The prediction error is supposed to be the clash between the physical sound and the psychic's prediction. But during an omission, there is zero bottom-up sensory signal. There's no physical sound at all. Therefore, a traditional prediction error signal technically can't be generated. This mystery severely challenges current formulations of the predictive coding framework. Now, to be totally fair, the neurofatigue model also heavily struggles to explain how a tired muscle somehow reacts to absolutely nothing happening.
The brain truly is an ever-evolving puzzle, and we are left with a massive challenge for future neuroscientists. How can the brain generate a prediction error or an alarm signal when there is literally no physical stimulus at all? I mean, how does pure silence trigger such a massive survival-level reaction? It really highlights the limits of current neuroscience and leaves us wondering just how deeply our minds are actively constructing reality, sometimes even out of thin air. Thanks for exploring the mystery of mismatch negativity with me today.